Welcome to Delta Computer Systems webinar. Today's topic is tricks for difficult systems, quick moves, I-PD, and gain scheduling. Thank you for joining us. This is just a quick reminder. We are recording this session and it will be available in a number of places following the conclusion of today's webinar. Today's presenter is Jacob Paso. Jacob is the Motion Products Development Manager here at Delta, and he is also heavily involved with applications engineering and support. And so with that, I would like to turn it over to Jacob.
Thank you, Aaron. Good morning, everyone. Today we're going to talk about some tips and tricks specifically for difficult systems, including what Aaron mentioned, and we have an additional one as well. So we'll be covering deadband tolerance parameter for oscillation, quick move, I-PD, and gain scheduling. We're going to move fairly quickly through the material, and we're going to be covering some advanced topics. We won't go through the basics. If you want more information, we have on our website the education page. We have some RMC tools training videos that are real good to go through. And we also have a new page on our website for webinars. You can look at that and see scheduled webinars and also past webinars. Especially the one about position tuning has a lot of good background information on the PID. So first, deadband tolerance is mainly used for overlap spool valves with deadband. And we're not talking about those today, but the deadband tolerance has a really good feature, namely that the integral gain only widens down inside the deadband tolerance. And what this means is that we can reduce oscillation when we are within the deadband tolerance window. So if we have a motion here, we have our target position, blue, and we have our actual position. Let's say we have a little bit of oscillation here at the end of motion as we're sitting still. At this point, the integral gain is typically winding up and winding down. Recall that we have a little error here. The integral gain will build up and build up. And then when it's large, the system will, of course, move the other direction. And now the integral gain is building up the other direction. And when we're talking about the 0 point of a valve when we're holding position, it gets really tricky. A valve can wear, it has a little bit of leakage, there's a little bit of hysteresis, it's not necessarily real linear. It's really hard to explain exactly what's going on. Sometimes we get this behavior here. And so if we can set up a deadband tolerance window around that position, where inside this window the integral gain does not wind up and wind down, then what we can get is the position staying much more steady within this small window. So the deadband tolerance can reduce small oscillations when holding position. It has a downside that it may limit the accuracy when you're holding position because the integral gain isn't fully working all the way in that range. If we can set the range small enough, then we don't really care about that accuracy. Let's go try it now. We have here a system, basic hydraulic system, 2-inch cylinder, 24-inch stroke bore. We see we just have a plate on it. We can move this back and forth. We have a rubber pad here at the end we can push in if we want to do force control. Right now we're just going to be doing position control. We'll set it down at the bottom of the screen and we'll look at RMC tools. And let's see, in RMC tools, we will open the plot manager. I'll start a trend here of axis 0. I'll do a move just back and forth. We can see the axis down here in the video moved back. We can see in the plot it moved back there. Now we move to 15 and we see that the position, the red line is up at 15. We'll stop that trend. Go back here, we see it move to 15. If I move the cursor over here and we look in the detail window over here, we see that the actual position is 15.000. And keep an eye on this as I move the cursor back and forth. That position is dead nuts on. So it's within 1/1000th of an inch. But if I now run a trend with a smaller scale, which I've already set up here, pause scale at 15, a real small one. look at what our actual position is doing, the red line. It's going up and down a little bit, so it's oscillating. If I put my cursor here, I see that my actual position is 0.0003, so a third of a thousandth of an inch, and then it goes roughly the same amount down. Now, in a lot of systems we don't care, but every once in a while we may have a system where this is a problem. So what we can do is set the deadband tolerance parameter. That is in the Axis Tools, in the Parameter section, down here on the All tab in the Output section. I have the deadband tolerance and the output deadband. The output deadband is what we use for overlap spool valves. The deadband tolerance can work with it or just separately, as we're going to do now. So if I look at this plot here, we'll put these above and below so we can see both of them a little bit. And we'll scroll down and get the output window. The deadband tolerance right there. I was going up and down about 0.0003, so I'll put it somewhere around there, 0.0002. We'll try that. Click the download button or Control D on the keyboard for speed. Notice all of a sudden that oscillation went away. If we zoom out, we saw we were oscillating. Now it goes away. We'll turn off the velocity here so we can see it a little bit better. Now it's fairly clear. It's one thing to do this right now. Hey, it fixed it. But what I really need to do to test it is move back and forth and see if it continues. So we'll move back to 1 here, click Ascend, and then we'll move back to 15. And we should see our position come back in here, and it looks like it's not oscillating there. Let's see if we're holding position though. Right here, if I put my cursor, we see the target position is 15.000. The actual position is 15.00016. So generally we'll hold tolerance better than what our deadband tolerance parameter is set to. And I see that I am doing that. I'm holding a little bit better than this tolerance value. So at this point, I'm kind of limiting my accuracy, perhaps, but I don't have this wide oscillation. So I'm actually overall much better accuracy than I had initially. So that's all there is really to the deadband tolerance and preventing oscillation. The valve I'm using here years ago, I started using it, really good valve, tuned up, great, held position. After a few years, I tuned it and it had this little small oscillation that I could not get rid of for the life of me. And I think it was just because the valve wore and who knows what's going on exactly at the zero position, and throwing in a little bit of deadband tolerance fixed it. We'll change the deadband tolerance back to 0 here and run, because for most of the things we're doing today, it won't make a very big difference. Next topic is quick move. Quick move starts in open loop and then decelerates to final position in closed loop control. Here's a plot of a regular move absolute command, and here we have one of a quick move absolute command. Absolute means that we're moving to an absolute defined position. If we say 7, we'll move to 7. Notice when we accelerate on the move absolute, we're in closed loop control. So we have a motion profile, the target's changing here, and the control output is changing to try to make sure we follow that. On the quick move absolute, we don't have a target we're following. We just set the control output to ramp up in a straight line to our max value, and then the motion does whatever it happens to do. And then once we're in motion, we have a target profile in the regular move that we're following, and the control output, it changes to make sure we're staying on velocity. Whereas in the quick move, we're in open loop. So we're just doing a straight open loop value, and you see that one's just flat right here. And then eventually we switch to closed loop control and move down. The RMC automatically calculates when to go to closed loop control based on your current velocity in the position and the final requested position. So on the quick move, why is it called quick? Let's see if anybody knows that answer. You can put your answer in the chat window on your GoToWebinar control panel. Does anyone know why it's called quick? We got one answer here, quick accel. Eliminate ramp up on the start. Yep, accelerates faster, 10 volts, max voltage equals quick. Absolutely. So both of those together. So you'll notice that I can ramp up this voltage to 10 volts. Whereas if I'm in a regular move command, I cannot bring it up to 10 volts because that's an error. Once it 10 volts, I'm not fully in control anymore in closed loop control. So the quick move allows you to do the full 10 volts, and you can ramp it up as fast as you want. You can put, almost infinity rate up here and ramp it up to 10 volts in one loop time of the controller. And so you get the total max speed there. That's why it's called quick. But besides being quick, what else is this good for besides moving at max velocity? Another big advantage is that we can use it when the axis controls poorly. And the whole reason for that is that all we need to do is tune it at the end, not for the whole move. I see a question came in here about the deadband tolerance. Have you ever had an onboard electronics valve with overlap overheat without deadband tolerance? I don't know. I myself haven't really had valves overheat that often, so I guess I'd have to defer to all our expert customers out in the field on that. But myself, I have not run into that problem, I guess. But back to the quick move here. When we have a system that controls poorly, it may cause all kinds of problems during the move, and most especially on the integral gain, and cause overshoot and undershoot and so on. If we get rid of having to control the beginning and just control the end, it can simplify some things, which is what the quick move is really good for sometimes. With the quick move, however, you have to beware of integral gain jump when going from open loop to closed loop. Here's a couple plots. This one is good. I've included the integral gain on there. There's just a little bump. On the other one, there's a big jump in the integral gain term. And that's not real good because that will cause overshoot or undershoot. And this can occur if the velocity feed forward is incorrect. When the axis switches from open loop to closed loop, it calculates what the control output based on velocity feed forward. And if that differs from the current control output, then the difference is put into the integral term. So the integral term can end up with a large positive or large negative value that can cause overshoot or undershoot. So that's the one thing we need to watch for on the quick move. So let's have a demonstration of this. We have our system there again, and we will look at it with RMC tools. Now on this system, this is a well-designed system. We have the valves right on the cylinder, good position, nothing funny going on with the load. So the quick move doesn't really help this system so much in terms of performance, but I've done some magic with user programs where I can run a bad system or good system. Right now we see there's a task running, it's running a good system. So if we start a trend and make a move, we can see that this system moves back and forth and it has very good control. There's nothing wrong with it whatsoever. Now, if we run a quick move, we will see how that works. So let's do a quick move to 1, and maybe we can do 10 volts. We'll ramp up at 1,000, decel at 200. Okay, now I made a classic mistake here. This is RMC 200 where the output is in percent, and I just did 10%. If it's 75150, it's volts. So I thought I was doing a full one. We'll do another one. We'll do 100%. And we'll move out to 20. So we see that I was able to ramp up to 10 volts, 100%, and move it at that speed all the way out. Notice the ramp is a little bit slow. We should be able to speed up that ramp. I'm at 1,000. Let's go to 10,000. I'll move back to 1. So now we have a much faster ramp, and we're able to get the full speed out of the system in the retract direction, and then it decelerated down into position. I see I'm overshooting a little bit here. I could probably improve the tuning a little bit if I wanted to. But this is a good system. Quick move can help us go fast. It doesn't give us much advantage because we can tune this very well regardless. So let's look at how this system behaves linearly. That's another thing that quick move is good for that I haven't mentioned, is to check the linearity of the system. What we can do is ramp the open loop voltage, and if it's a linear system, the velocity should also be linear. So let's try that out. We'll move to position of 20, I think, and we'll do an output rate of an output of 90, rate of 1,000, deceleration of 200. I wonder if that will work. Let's see. No, that didn't work. I need a slower rate here. 200 maybe. Let's see if I have a shortcut command set up to go to 1. I do. So I'll retract and let's try this. Okay, so I'm doing my control output ramp slowly so I can check the linearity of the velocity. And we see as my control output ramps up, my velocity is linear right along with it. So this indicates a good system. We also see that we have very little delay between the control output starting and the velocity ramping up. Some of this delay may actually be the filtering that we have in the plot here for the velocity. So this is a pretty good system. I'm going to change this task to run one that's always running a bad system. And then we'll see how this works. Again, running the same quick move where we ramp up to a voltage, and then it's nice, it stops me automatically so I don't slam into the end. Let's try that again. Okay, so now we see the control output ramped up, and notice there's a big delay before it starts moving, and then the velocity is not very linear. So this indicates that I have a bad system here. And of course, we're just simulating a bad system. So let's see what the quick move versus the move absolute does for us here. So if I do a regular move, we can probably increase the speed some. We see that the control output is going all over the place here. And it's kind of having trouble. Looks like it's controlling reasonably well on the end. Let's look at a plot where we actually have the integral gain included here. I have the output term in yellow. So we make a move back. We see that the integral gain kind of shakes around a little bit here and there. Let's see what it does in the positive direction. Let's see the 20 again. So now it's really kind of shaking all over the place and causing issues. And of course, we're not seeing huge overshoot on the end because I can only simulate a system that's so bad. But if we were to use the quick move, let's try that again with a quick move to 20 with 90%, and we'll do a rate of 1,000, deceleration of 200. Now, if I need to get it perfect, I don't have to worry about what's going on at the beginning of the move. I just have to tune the end of the move here. So let's look at that a little bit closer. I see right here when it switches to closed loop control that I'm getting a little bit of bump in the integral gain, but not so much. And then of course it's non-linear as it's decelerating, so I have some issues with that. But the integral gain is keeping me on the right side of the target, the undershoot, assuming that I can't handle so much overshoot. So I'm getting a little bit overshoot, but if I need to tune it, all I have to worry about is this section here. Now, I'm not quite sure exactly what I would do to improve this tuning a whole lot. We could try some motion here. If we decrease the velocity feed forward from 2.24 to 2, let's see what happens. Okay, we see that the integral gain jumped up a whole lot. So that was a wrong direction to deal with the velocity feed forward. Looks like we're getting some more overshoot. So we're at 2.2, was it? Let's go to 2.4. And I'll do a shortcut command back here just so we don't have to look at that motion all the time. Click ascend again. And now the integral gain jumped down, and that hopefully prevented this second side from going up so much and hopefully results in a little bit better control here. Just visually, it looks like it's a little bit better. I don't know how good I could possibly get it totally. The best fix for a system that really behaved like this would be to actually redesign the system and make it work better. But this should give kind of a little brief intro on what the quick move can do, what it's capable of doing. On a lot of systems that behave like this, we can spend lots and lots of time trying to tweak it. The nice thing with quick move is we hopefully spend a little bit less time. I see a question came in here. What physical aspects of a system would cause it to be bad, like your simulation? A few classic things are setting the valve far away from the cylinder, because now there's a time delay in the oil pressure wave going from the valve to the cylinder. You know, there's the speed of sound in oil and the speed of sound in air. It's only going to happen so fast. Also, hoses kind of can take things up. Probably the biggest thing is a valve with either overlap spool or weak solenoids. You know, we like to have linear motor valves with powerful solenoids and good control. But if you do have a lousy valve that's not real linear, that can behave very similarly to what I'm seeing here. Valves that are non-linear with weak spools, they may have one thing on their spec sheet, but then how they perform in real life can vary actually from that spec sheet more than what a high quality valve would. And someone commented poor lubrication on round way bearings. Yes, absolutely. There's all kinds of things in the loads and machine that can also cause problems. So next topic, I minus PD. Typically, we're always using a PID controller, and here we kind of turn on its head a little bit and use this I minus PD that we don't always use so often. But this is a different control algorithm that can be used for following a jumpy signal, and I say ensuring no overshoot. I should say help ensure no overshoot, because there's no guarantee. You can still get overshoot on it as well, but in some aspects it's a little bit easier. So there's some times that you may have an old system that you're retrofitting and it sends out an analog signal that tells the controller where to go. And maybe you're just upgrading the controller, put an RMC in there, and you're stuck with this lousy analog signal that hopefully looks like a step jump like this, but sometimes it kind of looks like this real messy one, and it's just a real challenge to follow exact and control. It's much nicer when things are done digitally rather than with old antiquated things, but regardless, we have to do that sometimes. So to help understand a jumpy signal, it helps to just consider a step jump, and we'll start looking at with a PID. And I'm sure many of you have heard me preach that we don't talk about step jumps with PID and high performance motion control, but today we're talking about lousy systems, so we'll have to put up with it. So with the PID, if we have our target, the blue line, the actual going up, something like this, and the control output is green, the classic thing is that the proportional gain will cause a huge control output spike, because the target and actual right at the beginning are very, very far away. So the proportional gain is going to give us lots and lots of control output. And then of course, the integral gain, typically being we have a lot of air here, is going to build that up, and then it's going to help us, cause us overshoot and so on. We can, add the differential gain and fix this and so on. But in general, these are the two main things that we deal with here. Now, the PID term versus the I minus PD. The PID adds the P, I, and D terms together. The proportional looks at the difference between the target and actual position. The integral sums that difference over time. And the differential looks at the difference between the target and actual velocity. And so it looks like what I just showed you earlier, we get this huge spike. Now with the I minus PD, we mainly use the I gain. We start with an I gain and then we subtract the proportional and differential. So with the I gain on the position, we'll have it go a little bit slower because the control output will rise a little bit slower because we're using the I gain. The I gain, it sums this difference up over time, and so we'll get a little bit slower rise on there. Rather where the P gain, it starts out kabang with a big jerk and then goes down. The I gain gives a little bit slower because it's slowly building that error up over time. Now, if we only had the I gain, it would cause oscillation. The integral gain, it would go up and then it would go down and up and down, and we just do this number forever. As we increase the integral gain, we would typically see a faster rise here, and then it would come down faster and faster. So as the I gain increases, we would see this oscillation speed increase. If we had a really low gain, it would be really slow and lazy. So what we do is we subtract the proportional term from the integral term. We do I minus P. So instead of having the integral gain go up real quickly, we subtract the proportional gain and it slows the rate of the integral term rise here. So we kind of more slowly come into this. And then if we increase the P term even more, it comes in even slower. So let's look at this one here. It came in pretty quick when we subtract a little bit of P term, but when we increase the P gain, now it goes even slower because we're subtracting even more from the integral gain. And then I don't have a nice slide for the differential gain, but it has similar type of effect. It affects the rate of how this goes on. Now, if we increase the I term, remember how I talked before, increasing the I term makes it rise faster and oscillate faster. So if we go back here where we increase the P term to slow down the I term more, and it takes longer to get in, to get faster, we increase the I term and then we get in there a little bit faster. In addition to this, the RMC adds a speed limit so that if you do increase the integral gain so that you have a really sharp rise here, we do have a speed limit that works on the algorithm to limit your rate of rise so you don't get a really fast jerk out of the motion. So with the I minus PD, the tuning procedure is basically to have some I gain and some P gain to start with. You need both of them for it to work. And we increase the I gain to get to position faster, and then we increase the P gain to prevent overshoot. And that's kind of an intuitive understanding of how the I minus PD works, and then we can look at the differential gain, how that affects it as well. But we can also just tune the system in PID mode and then use those exact same gains. I minus PD will work fine with those gains, especially if you use the tuning wizard in the RMC. It gets the gains set very well for that. It works great for this. So I minus PD is good for following a jumpy target, helping to prevent overshoot. And this, of course, is good for axes with difficult control as well. It's not good for following a defined target. We don't use the feed forwards here, so there's always a lag between the target and actual, and we can't define how quickly it comes into position. It's basically a result of your tuning how quickly it comes into position. So if you do have a defined target you need to follow, you would not use this. And it's also not good for synchronizing multiple axes because we cannot follow a target. So a lot of what the RMC does is high performance motion control. So typically we use a nicely defined target in PID. It's not all that often we have a need for an I minus PD, which is probably why you haven't heard about it so much. But let's go look at our system. and see how this works. Let's see, I have a trend here. Let's see, we have some user programs going on. A track minus I minus PD command. So here I use a curve that we've defined with the lousy system, or a lousy target, step jumps on the signal. And so we're going to run this curve as our target, and then we're going to have our axis track it using the I minus PD. So as user program, we'll just set the target on our reference, and then we move the axis starting position, start the curve on that reference, and we're going to tell our real axis to actually follow that reference. So let's look at that a bit. So it looks like I have a fairly high velocity limit on this, so the system's kind of shaking around. Looks like I lost my video on there, but we could see it shaking around there. So it looks like I need to fix my tuning there a little bit. We'll actually go back and set the gain smaller and actually do a normal tuning procedure on this. So I have a move absolute command here, moving to 1 and 1 to 20. We'll start with a little bit of proportional and a little bit of integral gain. We move to 1, and notice that it's kind of really slow and lazy. It took a long time for it to get there. Can't quite tell if we overshot because our plot isn't long enough. But we'll increase the integral gain so we can get to position faster. So I'll double it to 20, and we'll move to a position of 20. So we got there faster, but notice we're overshooting at the end. So I need to increase the proportional gain to prevent that overshoot. But that's going to get us there slower. So I'll increase the integral gain at the same time to get us there a little bit faster. Looks like we're getting into position a little bit faster there. We'll increase the integral gain a little bit more. And we are getting overshoot. So I'll increase the proportional gain more. And notice that all of a sudden it's taken longer here. So we continue this process of increasing the integral gain to get there faster. And we notice in the command here, I put the max speed at 20 in one direction, both directions are 20. And when I put my cursor here, I see the actual velocity, it has reached the limit of the speed. So it's actually right here going off the limit, and then at the end of that, I get the effects of the I minus PD. So we'll be able to see this final curve come in tighter and tighter as we increase the gains. So we'll increase the proportional gain a bit more and the integral gain a bit more and see what happens. Looks like it takes us a while to get in. Notice we're still running this bad system that we're having problems with. So it takes a little delay at the beginning before it gets moving, and it does jump on the velocity a bit. It takes I minus PD a little bit to deal with the fact that all of a sudden started jerking. But right now I increase proportional a fair amount. It's taken a long time to get into position. So I want to increase the integral a lot to actually be able to more quickly get into position there. And looks like it's getting a whole lot better. I'm guessing we can increase the gain a fair amount here. We may start overshooting though, so then I'll have to go back and adjust the proportional. We're getting a little overshoot here, so we increase the proportional some. And it's coming in there. So if I compare this, where we see it's coming in, it's not overshooting at all actually here, to a regular move command, we should see some difference. So let's do a regular move command. We'll move to 1 at a speed of 20. And, you know, we overshot there. Of course, I have the old gains here. That's kind of a bad deal. Let's see if I can get my original gains back. I have them stored over here. So we'll put the original gains back that I had for position control and move between 1 and 20. And I'm getting some overshoot at the end there. You know, the integral gain is probably winding up. We're having issues. If I move back to 1, we'll see I'm also having a little bit of trouble there. But if I go back to my I minus PD gains of 120 and 600 and 0 on the rest of these, and then do my step jump moves, we see here that we're actually doing without any overshoot. However, it is taking us a little bit longer to get into position here. So there's a trade-off with using I minus PD and versus PID, but this should give you a little bit of idea of what kind of things we can do with the I minus PD. I haven't talked about the differential gain yet. Let's play around with that a little bit, see what that does for us. I'll throw a value of 1. I wonder if that's too much or not. I guess we'll find out. So I have a lot of noise on my control output here, so I have to throw an output filter on that. Maybe 30 Hertz will be fine. And then we move in there. So I don't immediately see any really huge difference on the differential gain at this point. And I do have a fair amount of effect because we saw that it did affect the control output quite a bit. But if we increase that a bit, okay, now I'm starting to have serious problems. So that was kind of a bad thing to increase it that much. Now if we go up there, I'm guessing I should be able to increase the integral gain now and not have overshoot as much now that I have the differential gain. Looks like I'm getting a little overshoot on the other direction, and I see here I have a little bit overshoot, so that didn't help that much. If we increase proportional gain, we can probably get rid of that overshoot. So that's looking pretty reasonable right there. Someone commented here in the questions, I minus PD can be good for following a joystick input as well. That is entirely correct. Let's, after I tune this up a little bit, let's go follow that signal again. I'm going to throw in a little bit of slower velocity limit so it shakes so much. We'll download that program and let's run that curve again. Let's see, that was called track I minus PD. Okay, so now with the velocity limits doing a lot better following that profile. And we're not really getting any overshoot. If we do fast enough changes, it probably won't follow them, or it may have a little bit of overshoot depending on how quickly these motion changes come in there. Next item I want to talk about is gain scheduling. This is also for difficult systems. First of all, there's a question that came in. How do you determine if the output filter of 30 Hertz would work, and is that enough? Let's go back to RMC tools here. The loop time of RMC is 1 millisecond by default, so the update rate is 1 kilohertz. So we can kind of go off of that as to what might help. So any filter above a kilohertz is basically not going to do anything. We generally have to be a lot lower than that to have much of effect. Usually hydraulic systems have a lot lower frequencies, and we're typically looking at filtering out the noise. So usually a filter value about 100 Hertz is a good place to start, and then we decrease from there. A lot of times we can just start at 50 or 30, And that's on a lot of hydraulic systems. So these are kind of general numbers you can pick and choose. Start at 100 or 50. Generally, I go down a little bit more on systems I'm familiar with, like this one here. And in fact, I could probably bring it down a lot more than that if I really had to. So gain scheduling. On a lot of systems, even if they're not bad systems, gains or what the gains need to be can vary due to a varying mass. So if you have 1 pound on a system or 10,000 pounds on a system, it's possible that you may need different gains. Or if you have varying load angle, if you're pointing straight up or sideways or upside down, the load may need to change and your gains may need to change. And maybe you have a machine where your load angle actually varies on the fly. Or temperature. If you have a big difference in your controllability, if the oil is hot or if the oil is cold, you may need to have different gains. And there's more things that may require different gains. So gain scheduling is simply the process of changing gains on the fly as you're running to deal with some parameter, mass, load angle, temperature, that requires you to change your gains to have good control. Now, classic gain scheduling is basically like this. You have your varying parameter like load, and as that varies, you change your gain values. And I've seen some examples of this in the industry. Kabang, they change the gain values really quickly and abruptly. I don't like that. These discrete changes can cause problems. So what I prefer is having smooth continuous changes, and it's very easy to do that in the RMC using curves. So in the curve tool, we could tune a system in a few different places, whether it's different masses or positions or whatever, and we enter those values into the curve, and then it automatically interpolates nicely. So as this parameter, let's say its position, moves, that gain changes very smoothly so we don't get any step jumps or jerkiness in the system. So we only had to tune it at like 3 places, and then we get varying gains throughout the whole entire cycle. So let's go look at that system here. We have a different system set up that we can look at today. And this one is a swing arm system. The fulcrum is right here, and you can't see it in the picture, but the cylinder is right below here. It's mounted at the end here, and the rod goes right underneath. This I-beam is connected to it, and this thing will go back and forth. The swing arm, anyone who's been here for advanced training has played with this system here at Delta. And we'll connect to that other RMC. So I should have some motion commands set up here already. Let's see, we have some shortcut sets. Looks like we're doing a speed of 50, accel and decel of 100. So if I move to, let's say, a position of 90 with 50 and 100, we'll make that a little bit more visible down below. I'll click send, and we moved up, standing straight up there. Now, if we look at the plot, we see that it moved. I think I started from the end in open loop, so it behaved a little bit poorly. But if we do a few moves, I think we should be able to get a little bit better motion coming out of it. Okay, move down, the control's all right there. And then we'll move back to 90, standing straight up. Okay, so control's a little bit better here. But I want to point out something here on this system. On a typical move absolute, the control output is constant. But here we see that at the beginning it goes up because it accelerates, and that's also normal. But during the main moves, the control output becomes smaller and smaller. What's happening is that when it was down here at the bottom at a low angle of about 30, when we moved up, we needed a lot of force to move it up. But as we got closer to the top, we don't need so much force to continue moving it because there's virtually no load now. So the load changes quite a bit on this system, and we see that in the amount of control output that's required to keep a constant velocity. So this system is a great candidate for gain scheduling. We can change the gains here versus here versus here, and hopefully that'll give us a little bit better control. You notice here that we're not following so well at the end, and my guess is because the integral gain is having problems dealing with this changing system and causing the undershoot over here. Let's look at that with a different plot that I've included the integral term on, the yellow one, and we'll move back down to 30 degrees. See down here, it moves down low, and we see the integral gain kind of moves around a little bit there. And then if we move positive, we should see some issues there as well. And sure enough, so the integral gain is actually moving around trying to deal with that. So what I would like to do is do some gain scheduling here. What we do is define the gains at a few different points, and then we enter those in the curve tool. So we see here we actually have some curves that are for all of the gains. I think that's a little excessive. A lot of them don't necessarily need to change so much. Probably the ones that really need to change are the velocity feed forward. And if I look at my plots, we see this one, the control output changes quite a bit there. And if we move negative, the control output doesn't change so much. So I don't feel like that one really needs to change much in the negative direction, probably just in the positive direction of the velocity feed forward. It's a little bit difficult to determine what the velocity feed forward should be at any given point. With the tuning wizard, for example, but what we can do is just calculate it. If we look at the axis tools, tune tab, velocity feed forward, we see the units are percent per degrees per second. So that's just my speed. So it's percent of output per speed. So control output divided by speed. So the plot manager at this point here, I just look at my control output. It's 2.5 volts, which is 25%. And I divide that by my speed, the actual velocity, which is 49, which is about 50. So I can do that here and I can get a value. And then I can move my cursor over to the middle. And then I take my control output, that would be 2.7 volts, is 27% divided by pretty much the same velocity. So that's 27 divided by 50 roughly. And then I can move it here and I can do the same thing. The control output is 2.8 volts or 28% divided by about 49 looks like. Then I can take those values and put them in the curve tool, and I made another new curve here. And the results of those values I put here in the Y value, and then at the positions that I measured those, I put those in the X value. So we see this first point here was done at 38 degrees, and we determined the velocity feed forward should be 0.6. And then at 60 degrees, we determined the velocity feed forward should be 0.55. And then over at the end, we determined the velocity feed forward should be 0.46. So now what we need to do is make a user program that actually continuously assigns the value from the curve to the velocity feed forward. And we have here a user program that does it for all the gains. I made one that just does it for the single gain. So we see here that it's the axis zero velocity feed forward P for positive. And if we're here, if we actually wanted to create this, it's fairly simple. You just go to the axes, and this is one of the gains, so it's a parameter that's under control, and then we have the velocity feed forward positive. Double click it and it pops up there. Then the rest of it is using a function. It's called curve interp y. What that means is it interpolates the curve and gets the y value. So in the curve tool, we will enter the x value into that function, and it will give us the y value of the curve at any point. So curve interp y, And if I put my cursor, let's see, right there, we'll see that it's probably this one we're using. We need an ID value for that curve, which that curve ID happened to be 7. And then we give the X value, which is my position, the degrees. And then there's some options that define what happens when we're interpolating value that's beyond the endpoints. So I defined it from 38 to 95, but the system can actually move from about 20 to 115. And this option here, 8, actually just means we're going to extrapolate it. If I'm not quite sure about that, then I should be able to, on the functions, look at that curve interp y, click help, and in the help, oh, I get the expression editor, not that function, but I can look up that function here, curve interp y, and I get a full explanation of it. We see the options here. Number 8 is extrapolated, which is the one I'm using. So we have 8 there. And so this user program is just one step and it's continuously repeating. So it's continuously looking up the value in the curve based on position and putting that in my feed forward. I need to make sure to run it on its own task so nothing else steps on it. Go ahead and download that and we'll run it on task 1. Let's see, that was my gain scheduling. So now it's running, and in the plot manager on the tuning tab, we can see this velocity feed forward is yellow because what's in the controller is continuously changing, so it's different than what I have in my project. So that's continuously running. So now as I make motions, that velocity feed forward should continuously be updating, and I should see a little bit difference in my control. So let's go move it back to 30 and see if this changes anything. Of course, in that direction, we're not using feed forward positive, so we shouldn't see it. But let's move to 90 and we should see some change here. Okay, so I think this control output is changing a lot less, or sorry, the integral term is changing a lot less than it was before. Let's go look in the history, compare that one and this one. So here, the integral term was very large negative. Here, when we had the feed forward set better, the integral term didn't have to do as much work, and we're having less undershoot problems at the end. We're actually overshooting a tad bit, whereas here we had undershoot, no overshoot, but all in all, we're getting a little bit better control here. Now, if I fiddled with this a little bit more, I'm sure we could improve that control better yet. But this does give a pretty good demonstration of what the gain scheduling is and what it can do for you. Now, sometimes on a system, if you know ahead of time that your mass is going to be changing for a certain cycle, you just write to the gain beforehand and you don't have to continuously update it. But if your load is changing on the fly, like our swing arm system does here, then you can have this user program system where it's continuously changing the gains on the fly. There's a few things involved with actually having a user program running. You need to make sure that you're not using anything else on that task. You need to make sure user program is only one step and continuously repeating, so you're updating it every loop time. And you also may want to check to make sure that that user program does not automatically stop when an axis halts. That's in the programming. If I right click and choose properties and we look at halts, by default, if any axis halts, we stop all the tasks. So that means all the user programs stop. But sometimes you have a task that you want to have running no matter what. So you can choose to stop the following tasks and you uncheck the one that you want to run all the time. So in our case, we want task 1 to run all the time. It's not doing any motion, so it's not going to cause any problems if an axis halts, but we do want it to be running and not just randomly stop. So we can click OK. And of course, we have to download that. So downloading it will actually stop all my tasks. But if I start that up and run that again, now if I happen to have a halt on the axis, that user program will still stay running. So that's about it for today. We've looked at a few tips and tricks: deadband tolerance for small oscillations, quick move for speed or for difficult systems, I-PD for jumpy targets, and gain scheduling for varying gains. If you have any questions, now is a very good time to enter those into your chat, and I can see them here and we can try to answer them. See, one question came in: would it be better to use gain scheduling for heavy loads with short moves or just use quick moves? You know, I'm not sure I can answer that just right off the bat. You probably actually have to run the system and see which one would work better. But you are entirely correct. You know, we have gain scheduling here to deal with some issues, but a quick move can equally well deal with that issue because now you're not tuning most of the motion. So you certainly can use multiple ways to solve a problem. Another question came in: it seems like you're always trying to make the integral term be very small. Is this always a good thing to look at and try to minimize? Yes, you probably noticed one of my favorite things to do is look at the integral gain. The integral gain is very, very good at holding final position, and it can help us track during motion, but if it winds up or winds down, that simply can cause problems, and that is often a very major issue. So yes, if you get in the habit of being able to look at that, that can certainly help. Any other questions? And remember, Delta Technical Support is only an email or call away. And I also want to bring your attention to the hydraulic design guide. You can go to Delta's website. It's on our home page. Looks like this, says free design guide. If you enter your contact information, we will email you a real paper copy of the design guide that will help you design a system that works very well, so you hopefully don't have to use I-PD or quick move or deadband tolerance or maybe even gain scheduling because their system's designed so well. Any other questions before we end? Okay, thank you very much for attending the webinar today. As a reminder, you can sign up for the design guide on our website, and we do have on our website a webinar page in the education section where you can view this webinar that has been recorded, and it should be up there in just a few hours. So you can look at this later, or you can pass this link to other people you know who may want to learn the same information. Thank you very much, and have a good day.
Thank you, Jacob, and thank you to all of our attendees for joining us today. We really appreciate it. And as Jacob mentioned, deltamotion.com, education, in the education section, you'll find the webinars page. Again, as Jacob mentioned, we're going to try and have that the recording put up there as soon as we possibly can. Also, if you're not familiar with our forum, we have forum.deltamotion.com. We have a Delta webinars topic. The recording will be there as well. And then if you're not familiar with us, we have a YouTube channel as well on youtube.com. Look for Delta Motion Control. That's all one word. And recordings will be there as well. You will receive a link to a survey at the end. That really helps us out because that gives you the opportunity to kind of give us some feedback. That's your opportunity also to let us know if there are some future topics that you'd be interested in hearing about. So if you could fill out that survey, that would be really helpful for us. Thanks again, and we hope to see you at the next, we hope to have you join us at the next webinar. Thanks.